Chapter 15, Part 4, we are going to talk about independence. So far we have learned that when finding the probability of two independent events, we multiply their probabilities. But what happens if the two events are not independent? So if A and B are independent, and we're finding the probability of A and B, we said to take the probability of A and multiply it with the probability of B. If A and B are dependent and we're finding the probability of A and B, we need to use conditional probabilities. So we said that we would take the probability of A, multiply it by the probability of B given A. Now, we've already seen this formula in action when we were working with probabilities that did not involve replacement. So you were holding on to that card and keeping it in your hand before choosing another one. In some scenarios, it can be difficult to determine whether or not two events are independent or dependent, so we'll talk about a few formulas here that can be quite helpful. So the first part here, what does it mean to be independent? Remember that independent means that the outcome of event A does not impact the outcome of event B. Whatever happens in event A is not impacting our chances of event B occurring. If two events are independent, then the following formulas will be true. The probability of A should be equal to the probability of A given B. If A and B do not impact one another, then it shouldn't matter whether B has occurred or not. The probability of A will be the same as the probability of A given B. You could also switch this, so we might write it as the probability of B is equal to the probability of B given A. Again, A and B are not impacting each other, so the fact that A has already occurred and it's our condition doesn't matter. It's still equal to the probability of B. Now we do want to know these formulas. Sometimes questions will simply just ask you to determine if two events are independent. If you set up this formula and the two probabilities are equal, it means that the events are independent. If you set up the two probabilities and they are different, they do not equal each other, it means they are not independent, proving they must be dependent events. We also want to talk about whether or not events are disjoint or mutually exclusive. Remember that if two joints are mutually exclusive, it means that the two events cannot occur at the same time. We've also said that mutually exclusive means there's no overlap between the events. So if two events are disjoint and there is no overlap, then the probability of A and B occurring, probability that both events happen at the same time, should be 0. If the two events are not disjoint, then the probability of A and B will be something other than 0. So I'm going to say that the probability of A and B should be greater than 0, but it's a probability, so it needs to be less than or equal to 1. So this is just the fancy math way of saying that it's somewhere in between 0 and 1. Let's go ahead and look at example 1 for an example of how we can use these formulas in context. Example 1 says, a survey found that 56% of college students live on campus, 62% have a campus meal program, and 42% do both. Are living on campus and having a meal plan independent? And we want to answer if they are disjoint. Now, I'm noticing that there isn't a picture here. I like to draw a Venn diagram. The two events that we're looking at will represent my two circles in the Venn diagram. I'm looking at kids that live on campus, so I'm just going to do L for live on campus. And the other one's talking about a campus meal program, so I'm going to put just an M there for the meal program. Remember that with these Venn diagrams, we want to start with the middle, so I'm looking for % of people that have a meal plan and live on campus. That's my 0.42. It says that 56% of college students live on campus, so this entire circle needs to add to 56%. I already have 42, so 56 minus 42, would give me 14% here. 62% have a meal program, so this whole circle should add to 62. Again, I already have 42 in the middle, so I should have 20 left over. If I want to find out what's left on the outside, so these would be students that don't live on campus and don't have a meal plan, I'm going to take all of these and subtract them from 1. Gives me 0.24. Now, the first thing I want to do is answer whether or not these events are independent. Now, there's a few ways that you can solve this. It's really up to you. You can either try to show that the probability of living on campus is equal to the probability of living on campus given you have a meal plan, or you could go in the opposite direction and show that the probability of having a meal plan is equal to the probability of having a meal plan given you live on campus. For purpose of this notes, we'll go over both. If you are asked to determine if they are independent or not, you would only have to show one. So the probability that someone lives on campus is this entire circle. They gave it to me here. They said it was 0.56. The conditional probability I'll have to solve myself. So I'm starting with the conditions that they live on, or they have a meal plan. So I'm looking at just this circle M. In total, that would add to 62. So the 0.62 would be my denominator. Now, just out of that 62%, how many people live on campus? That would be just this overlap here, so the 0.42. I'm going to go ahead and type in 0.42 divided by 0.62. Why am I doing that? Gives me 0.6774. Okay, that does not equal 0.56, so that would be enough information to show me that these events are not independent. So I could say that living on campus and having a meal plan are dependent events. Your work might look different. Maybe you wanted to use this formula here, so we would have the probability that someone has a meal plan. That's all of this circle M, so that's 0.62. Then I would be finding the probability of a meal plan given they live on campus. So I'd be looking at this circle L, so I'd have 0.14 plus 0.42, which would be 0.56. And I'd only be looking for those that are also in M, so that would be 0.42. Again, typing that into my calculator gives me 0.75. Either way, they're not equal, again, showing that they are dependent events. The other question wanted me to find whether or not these events are disjoint. To find whether or not they're disjoint, we need to find the probability of both events occurring. So that's living on campus and having a meal plan. They gave this to me right here. I can also use my Venn diagram. It's 0.42. 0.42 is not 0, so that means that these two events are not disjoint. So in context, I would say living on campus and having a meal plan are not disjoint. This means they can happen at the same time. You can have a meal plan and live on campus. Go ahead and pause your video to try this next problem on your own. Once you are done, go ahead and play your video to check over your work, comparing it to mine. Here is my work for that next example. I tried to show both ways that you could try and prove independence. Either way, when you solve them, your two probabilities, although they're not exactly the same, they are very, very close. It's close enough to say that they are independent. Again, these two things should not be disjoint. They're not disjoint, not mutually exclusive, because the probability of both having a blood test and a breath test was greater than 0. Okay, we'll look at example 2 together. Similar kind of problem, it just gives us a table instead of a Venn diagram. So we're looking at the probabilities that an adult American man has high blood pressure and or high cholesterol. We want to find whether or not these two things are independent. So I'm only going to go one way. Let's try and show that the probability of high blood pressure, so I'm going to put just BL for blood, is equal to the probability of high blood pressure given that they have high cholesterol. So the first thing I would need to do is to find the chances that somebody has high blood pressure. So looking at my table here, here's my blood pressure. All of these guys here have high blood pressure. So adding those together would give me 0.27. And the next, I'm looking for the chances that somebody has high blood pressure given that they have high cholesterol. So I'd have to look for high cholesterol first, which is this row. 0.11 plus 0.21 gives me 0.32. And just out of that 32%, I'm looking for high blood pressure, which is the 0.11. So typing in here, 0.11 divided by 0.32, we get 0.3438. These are not equal. They are definitely not even close. So I would say that high blood pressure and high cholesterol are dependent events. Go ahead and try the next problem here. Again, gives you a table. This time it is just numbers instead of the percentages, but same kind of process. 2 questions. You want to again find whether they are independent or not, and then also determine if they are mutually exclusive. Here is my work for this problem. This one was just asking if party affiliation is independent of the respondent's gender. So there are tons of different options. I chose to look at Democrat and male, but you could look at female Democrat, female independent. There's tons of options for you here. So your work may not match mine exactly, it's depending on which variables you chose to look at. When I was finding the chances of somebody just being a Democrat, I took the total for Democrat over the total number of people that participated. Then I found the chances of someone being a Democrat given that they are a male to see if male had any impact on being a Democrat. So I needed to look at males first, which was 105, and again, 36 of them were Democrats. I found that these two probabilities were not equal, so the events are dependent. Regardless of what party affiliation or gender you looked at, you should still get two probabilities that are not equal, showing you that they are dependent events. To see if they are disjoint or mutually exclusive, we would find the probability of the two events happening at the same time. So I'm looking for Democrats and males. I can clearly see that there are Democrats who are males, so this would be 36 out of 202, which gave me a probability greater than 0. So these would be not disjoint. Again, regardless of what party or gender you chose, you should still get a probability that is greater than 0. All right, the last problem we have here is example 4. This gives us the probability of A, the probability of A given B, and then the probability of A and B. We are asked whether to find out whether or not they are independent and if they are disjoint. So it looks like they are giving me the probability of A given B. So I'm going to use that there for my independence. If these two events are independent, then B should have no impact on A. So this should be equal to the probability of A. Well, A given B was 0.5. Probability of A was 0.7. These are not equal. So these events are dependent. If they're disjoint, I want to look at the probability of A given B. They tell me that this is 0.2. That's greater than 0, so they are not disjoint. They have an overlap. They can occur at the same time. Hey, part B is kind of tricky. It's asking me to draw a Venn diagram to represent this data. So I'm going to go ahead and put my box in the two circles for event A and B. We're going to start with the middle. They gave me A and B was 0.2. They also tell me that all of A is 0.7, so this whole circle should add up to 0.7. I already have 0.2, so this would be 0.5. Now, typically what happens is the problem also gives you just the chances of B occurring. They give you the whole probability of B. But in this case, they don't tell us that. The only other thing that we have is A given B. So what I want to do is use this A given B to hopefully somehow find what's left over. Now, when I'm finding the probability of A given B, the condition is B. So if I'm thinking about my Venn diagram here, I would start with finding all of B. That means that my denominator would be the probability of B. Once I've located that amount, I then look for the percent that's in A, which would be this overlap here, which notation-wise we call the probability of A and B. Now this can look kind of confusing, but if you pay close attention, we actually have 2 out of the 3 of these probabilities. We know that A given B is 0.5. We know that A and B is 0.2. The only thing we don't have is this probability of B. To get that probability of B by itself, I would start with multiplying the probability of B on both sides. I would then have probability of B times 0.5. To move that 0.5 over, I would divide. So I would end up with 0.2 over 0.5. Plugging the 0.2 over 0.5 into our calculator should give us 0.4. Now that I know that all of B is 0.4, and I already have the 0.2 in the middle, this gives me 0.2 in B. Again, I know that all of these need to add to 1, so if I do 1 minus 0.5, 0.2, 0.2, I'm left with 0.1 on the outside.